Hey, good afternoon. We're going to get started in just about 1 minute. Okay, so it is 2 o'clock. I didn't give us quite a minute. I think there'll be a few people that'll log on as we go. And good afternoon, everyone. Thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is turning power quality measurements into actionable information. It's being presented by Frank Healy from Fluke. Frank has been the power quality product marketing manager at Fluke since 2006 and has been in the industry for well over 3 decades. He globally manages Fluke's power quality products, including measuring instruments and precision power analyzers. Frank's lengthy career has allowed him to witness the progression of the industry, and he has long worked at raising awareness and understanding of power quality. We expect today's presentation to last roughly 30 minutes, and then we'll answer any questions that have been submitted during the presentation. At any time, you can send questions through the question box to the right side in your webinar controls, and then we'll review them at the end of the presentation. I also want to mention that this webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Frank.
Thank you, Nicole. So hopefully what we're going to do today is go through some real basics of what power quality and also energy measurements are about. And even if you aren't using a Fluke product, hopefully these principles will help you to really get to grips with reporting of data and also being able to share that data and to create stories which will be able to share with other people so that you can explain exactly what's going on. I know typically most people are given the task of going to find out what's going on, and normally they have to come up with a solution. Often they have to share that with other information, with other people, and maybe sometimes have to make an investment to fix the problem. So having a good story behind that investment is obviously really important. The key thing here is that what we're primarily looking at is the software which will enable you to do that. I will talk something about the principles of making good measurements, but primarily this is going to be about the software and how we can turn measurement data into useful information which can come up with real solutions for you. I'm just going to clear my throat one moment, so I'm just going to put on mute. Okay. So we're going to see hopefully how we can use things like voltage trends and current trends to see the natural rhythm of the electrical system, which you can start to share with other people, and kind of that helps explain. Even a layman can kind of understand this often. Then we'll also talk about how electronic equipment is a source of power quality issues, but sometimes can be a problem for the systems as well. So on the one hand, you may have an electronic load which is creating harmonics, and right next door to it you've got another load which is suffering from the effects of that. Then we'll talk about how baseline studies can be used to discover how your power quality or energy trend is going, so that you can discover whether you're getting better power quality, whether the measures you're putting in place are working, or whether they're just degrading still. Then we will see how we can compare measurements from locations in different time periods so that we can start to improve power quality and discover how we can correlate what's happened in the past with what's happening now, and hopefully find out where the trend is. Is it going up or is it going down? Is there something that you've done to improve things, or is something been installed which is causing the problem? And then we will see how we can share that data with other formats which can be used for more advanced topics like modeling of systems and sometimes proprietary data analysis, where users have their own software that they prefer to use, and how we can get that data out of the software and what you need to consider when you're doing that. So the first thing I would say is that we should always be thinking about creating pictures. These are really powerful things when we start to explain things to other users. If we have a picture of what happened, it's much easier to understand than many words. So having pictures in the software which will describe the situation is really useful. So for example, here we have this example where we're seeing a whole process which has happened over a long time. This was a study which was done over something like 42 days. And you can see the rhythm there. We can see that typically during the week we have steady consumption, then we have a gap at the weekend, mostly, because there's some exceptions in this. But we also see where we get some peaks that we might not be really considering. And if you're a large facility, some of those peaks may be costing you. Often large utilities or large facilities have a contract with a utility which is based on peak demand. That's how much energy they will take out of the system. So having information about what you're really using the energy, when you're really using the energy, and whether you're going over the peak demand is extremely important, because without that you won't know when you're going to exceed the limit. And when you exceed the limit, you can pay penalties, and the penalty can be very severe. It's not just a penalty based upon paying for that extra energy. There is an additional penalty on that, and often that would go on for a full 30-day period. So the utility would charge you at that higher rate for a full 30-day period. Typically, these peak demand processes look at something like a 15 or 30-minute period, and they will measure the kilowatt hour over that period. And for the benefit for the facility to take up that kind of tariff is that they get the energy at a better price, because they're committing to taking a certain level of energy from the utility, which enables the utility to plan their network better. Some of the users who have this kind of peak demand type of tariff, they also consider having loads which can be taken offline at any time to make sure that they don't exceed those limits, and they can be automatically switched off. So it may be things like large pumps or different kinds of motors which they'll take offline, or heating loads, compressors, those kinds of things, which might be taking them close to the limit, but they will switch them off to ensure that they keep below the level that they've agreed with the utility. So one of the things to consider when we're looking at this is that you can see the pattern, but often it's very useful to speak to the users and ask them how they see the pattern. Does this match up with their expectations? Within our company, we're part of a larger group called Fortive. We've done studies on a lot of our facilities in different parts of the US and other parts of the world, where we have an expectation of what the energy bill will look like, and then when we go and look at it, we get a surprise, and usually it's not a good one. So we've done multiple studies in our facilities to see why we're getting those high bills. And often it's because the system's had lots of adds, moves and changes made to it over a long period of time. So we've found out things where the users have asked for cooling during the summer, and they get that because they're in a hot environment, and they install some chillers to cool down the work area, and they end up running during the winter. And at the same time, they're not really well controlled, and they're putting on heating during the winter. And then they have these systems working against each other. We also had systems which were venting when they didn't really need to do, so they were taking heat out of the environment where people were working, and then we were compensating for that using heating. So asking questions about why people take those actions is really important to get to grips with the story that you're hoping to tell, because the story will mean everything. Just kind of looking at some numbers on a chart or a graph doesn't always really tell the story. It needs some explanation behind it. So here's one of the simple things that we use. This is a calendar kind of view. So here we're looking at an electrical system which has a particular rhythm. This is just on a daily basis. So we see typical daily thing from midnight up until maybe 4 or 5 a.m. There's not very much power being consumed, and then suddenly things get switched on, and we have a peak at the beginning of the day as lots of machinery comes on, and then heating loads go on, and it starts to settle down after that. And then it has this really reasonably steady period during the day on each of the days. And then we see that when we get to the weekend, we see a different pattern. In this case, this was an exception. So we had Monday where they were actually had a holiday in this particular case. This was done in the UK, and they had a holiday, and they started up a late afternoon run of production on Monday afternoon. And then to compensate for the shorter week, they actually had to work the Saturday. So you see the Saturday profile. But then Sunday, they didn't really do as much because some people were in the plant doing regular work, maintenance and so on. So they were switching on some loads. And then on the Monday, that started again at the typical time, 4 or 5 a.m., but we didn't complete beyond that time. So we see that work a week pattern and how the daily rhythm operates in the facility. In this case, this was energy consumption, but we also see the same thing when we have power quality problems. They normally coincide with this kind of pattern. So we normally see power quality problems come on when particular loads are switching in the network. Again, we're now looking at trend charts and graphs, and these are really simple, and this is some basic information. It's telling us about the trends, but what we're really interested in here is recognizing those basic trends and recognizing the patterns. And again, it's about asking the users about their day. What would they expect to see when the guy comes in early in the morning? What does he actually do? You know, which loads does he switch on? Which are the energy hogs in the facility? Which things cause that early morning peak? And once you understand what those loads are, it becomes a lot easier to understand why the pattern of the energy consumption or power quality problem sometimes. So you have to become somewhat of an investigator. You have to know the right questions to ask. Most of them are very simple questions, but it starts to enable you to create the story behind the graphs. And then when you show the people who have asked you about what their energy consumption looks like, and you show them the graphs, they get it. It's really straightforward. You know, so you can identify which loads come on at which time. The reason why we're interested in that is that we're looking really for exceptions. Why has something happened that we don't expect? Because that's an opportunity for discovering a power quality problem or discovering an energy savings issue as well. So you need to compare the values to correlate. It's normally if something happened, something else happens. So you have to look from multiple viewpoints to be able to see what happened. And in this case, with the top graph is just a plain vanilla trend of the RMS power. And then below that, we've got the voltage and current on one of the phases. And what we see is that we're getting lots of current peaks. We have this switching current, which is going on very, very frequently. And we also have, those are the gray bars. And then we have the black bars underneath that, which are the pattern of the voltage during the typically on one of the phases. And there we see the same kind of pattern as to the voltage. So we see that although the current is being drawn in this nasty way, and that's because it's a set of compressors which are running fairly frequently in refrigeration equipment, but we see that the voltage is dropping and it has this particular pattern, but it's not really that big a problem in this case. We're not drawing that much current to cause a real problem, but we need to look at that just to make sure that we aren't causing those problems. So here we have an exception. So this is we've zoomed into the graph and we're looking at just one particular portion of the graph. And what we can see here is that we're seeing a higher current at a time of day that we don't expect. And this is the time to ask a question. You know, the question is, what was going on? Was there anybody in the facility at that time? Did somebody work late? Is that why this current was drawn in this higher way than we'd normally anticipate? It's not like the other days. So why was it happening? It may well be that it's some kind of load which is not set up properly and it's turning on at the wrong time. Or it may be completely valid. But again, ask the question, because if you start to see this pattern every day, when the facility is not operating, then you need to discover why that would be, because that's an energy saving opportunity. You don't want loads running when they shouldn't be, when you're not getting useful production out. So having the ability to look at the loads in this graphical way, you can start to see the pattern of the facility and look for the exceptions. That's the really useful thing, to look for the exceptions to build an accurate story. So here we've got a real horrible looking picture, but this is just instructive as to how to create the picture. So we have the top graph there, which has just got too much information in, and you need to zoom into the picture to be able to see some of the interesting things. So you need to look maybe just by day, for example, or it may even be by hour. It depends how long your study is that you're doing. But we've got a lot of information on the top graph, and it's not really helping us. So you have to choose your scaling to make sure that you're looking in the right time domain, if you like, so that you're looking not just at several weeks of data on one graph and hoping that's going to tell you what's happened. You need to zoom down to a level which will really give you some better idea as to what's happened. And on this bottom graph, what we can see is that we can see voltage, which is the black signal, and we can see the current. And we see a current trend where when the current's low along the bottom, that's kind of the pink trace, we see the voltage goes down. That's kind of normal because that's the activity in the facility. You'll usually see voltage drop caused by loads coming on and current going up. So there's a direct correlation between the voltage and the current. So just looking for those is important. What we don't want to see is we don't want to see the voltage going down really significantly below the level that we'd expect when loads switch on. That could be an indication that we're overloading the circuit, or that the facility is overloaded, where we're drawing too much current and the source of the voltage doesn't have enough capability to supply. Because at that point, then you may be getting voltage dips, you may be getting sags on the voltage, which would cause problems for equipment. Maybe they'll just reset accidentally, or maybe breakers will trip because of that. So these pictures at this level are really important to best understand. So here we're looking at some harmonics on the other side, but what we're going to talk about is benchmarking. So this is making comparisons. So the idea behind a benchmark is that you start off with what you would describe as being a good situation. Now, it may not always be good, but you look at the first situation first and see how that looks, and then start to make measurements over different times or in different locations. It really depends. It may well be that you've got many identical loads which should perform exactly the same. So you would do a campaign around that one piece of equipment and then compare it to the others to make sure that they're all performing in the same way. And then if they're not performing in the same way, then you then look at as to why that might be. So, for example, may well be that your equipment is malfunctioning in some way. It may be that it's not been set up in the right way first time round. So having the ability to be able to take a look from either time to time or location to location is important, because the best way to look at this is that you should be looking for the best situation. So if you can find the best operating load and look at the way that's set up, then that's the one that you should try to be set up like. That should be your best case. And of course, you may be also hoping to discover what's the worst case and then get the opportunity to put that right so that it's not causing too much energy consumption, or it's not causing too much power quality issues. So having those benchmarks and comparisons will help you find the best way to go about running your facility and running the electrical equipment, and also sharing that with other people, letting them know why that might be. In this case, we have a simple, on the graph here, we have simple, you can't probably see the detail too much, but here there was a installation of some filters. So we have high harmonics on the top graph, and they've been reduced in the bottom graph. So we have a reduction. So the scale here at the top is 3.6, and then on the bottom graph it's 2.4. So we've reduced the distortion caused by harmonic load, which was of concern. So next we'll talk about the tabular data. So this is looking at long lists of numbers, and this can be potentially very kind of difficult, time consuming, not very helpful. This is really looking at data in just this way can really take up a lot of time, and you don't really tell very much. In this example, though, what we've tried to do with some of our software, and many other software packages do the same thing, is that they look for the worst cases. So in this case, we're looking at the power. So we're looking at power, apparent power, non-active power, that's K of R or VAR, and the power factor. And this has been documented for us by the software to show us when the maximum values occurred across each of the phases and also the totals. And it gives us a timestamp with that as well. So we can see this in a graph, but this gives us the absolute information. It's not just kind of looking in the graph and seeing that, kind of what looked like Monday morning was the time. Here we have a timestamp against it. And then we start to see timestamps which are all match, which in this case we largely do. So we see that the maximum power on all three phases was the same as the total maximum power time. That tells us that we have a balanced load. So we're not really taking too much off one phase or the other. We've got something going on simultaneously, which is kind of happening across all phases. And then we also can see what the average is. And on the averages, we see, for example, that there is a difference on the averages. We go from 17 to 25 kilowatts in this case. So there are some single phase loads on some of the phases in this case, which are drawing more. It just tells us that probably whoever installed the equipment in the first place decided to site the equipment on phase C rather than phase A. And then the last one is that we have minimums, and we see the minimum is fairly consistent apart from on phase C. So that highlights something happening on phase C for the active power. So we have 10 kilowatts being consumed as a minimum on phase C. And on phase A, we've only got 2 kilowatts. So that phase C is more heavily loaded. And it may not be a problem this time, but it's something to consider for the future. If you have an identified problem with maybe a breaker tripping on that circuit, that could be the important clue that kind of leads you to find out why that would be. And the same applies on the apparent power and so on. So the idea behind the table is that, yes, it's lots of detail, but also it's summarized in a really comfortable way so that you can make some use of it. So when we come to doing power quality reports, standards are really important. So standard is not necessarily something that is detailed by an organization. There are many organizational standards like IEEE, IEC, but the important thing is to do the same thing every time. That's really the most important thing about a standard, is that it will allow you consistency in terms of your measurement. So this is one of the presentations of data that we provide with our instruments or with our software. And on here we can see a lot of readings. Here we've got hundreds of measurements. Sorry, we've got thousands of measurements of hundreds of types, and we're presenting on this simple graph. So we have examples of where we're measuring frequency, voltage variations, voltage harmonics, unbalance, and events. We're putting those into this presentation where we created what we call a limit line. So that's the dotted line. So the limit is something that would be set beforehand. So the limit in this case for voltage variations is plus minus 10%. It could equally be plus minus 5%, but in this case it's plus minus 10%. And we see that we have a red bar on here. And the red bar is exactly what you would imagine. It's an alert. It's telling us that there's a problem. So this is telling us very quickly that there is a problem on phase A for voltage variations. So the other green bars means that we can ignore those for now. We don't really need to dig into those too much, and we should investigate further into the red bar. So that's what we do. So we go to the red bar and we drill down to a different level, and we select the red bar, and we can see that when we look at the bottom graph here, that we can see that we have the limit line. You can see the pink line at the top, And what we can see is that the black trace of the voltage is going through that limit line at certain points in time. So we have voltage swells on this circuit. So just this one circuit as opposed to the other. Now that tallies with what we saw previously, because we saw that phase A was the least loaded phase. So the other phases were more heavily loaded. So the voltage on those circuits wasn't going beyond the limit. And if we were to look at phase C, for example, we'd probably see that that was well within the limit, because it's kind of quite well loaded. So by drilling down into the information, we can take this information and use it as part of the story. And it's always useful to have these pictures to use. So as you go along, make copies of the pictures, either just by doing screenshots. In our case, we have what we call bookmarks. So we can take this picture of the screen and use that as a bookmark, which will go into a final report. And then another drill down, here we see that we're looking at the events that happened. So these are the voltage variations. And here we have an absolute count of what they were. So it tells us that we had 17 events. The other thing that it tells us that we have a type of event. So we have interruptions, swells, and dips. In this case, we had 17 events outside the limit, and they were all swells. And the worst case is here that they were bad because they were greater than 1 minute each, which is not a good situation. The reason in this case is that the location of this plant was being redeveloped, and some of the other nearby loads have been taken off the system, and that caused an overall voltage rise. So the voltage at the incoming power supply for the facility was higher than you would expect. If that continues to happen, they would have to talk to the local power company and get them to adjust the voltage regulation on that transformer to make sure that they weren't going too far above those allowed limits. And here we go right down into the details. So here we're looking at when we see the swell, when that happens. So this is an RMS trace over time, very detailed view. It could even be more detailed than this, and it could be down to the waveform level in some cases. But again, it's documenting, and it's seeing exactly what happened and making sense of what's happening. So let's just have a quick word about harmonic sources. So we have in power quality problems with harmonics. So voltage and current harmonics are present in power systems, and these are multiples of the frequency. So typically we have 60 hertz frequency, but the harmonics are multiples of those, and they're caused by electronic loads. So the way that the electronic loads work is that they take out the current out of the system in kind of gulps of current. So they're not always taken out at 60 hertz, they're taken out at much higher frequencies. So the most common harmonics that you'll see are odd multiples of the power frequency, such as the third, the fifth, and seventh. Mostly we see that the fifth harmonic is kind of the highest one, but often third harmonic can be. It depends upon the types of loads which are in the facility or in the area. So the reason why these harmonics are so prevalent now is because of the kind of rise of electronic equipment and the number of pieces of electronic equipment there are, from everything from drives, power supplies, UPS systems, all of those things. They take out the current in that way, and they cause distortion. You'll always see the distortion, and here we can see in this example with the waveforms, we see the current is very distorted, and we see that the voltage has flat top on it because of the harmonics. It's misshapen, the typical sine wave we should see. So when we come to sensitive loads, if we look in something like a data center, so here we have a data center which has probably lots of backup, and it has sensitive equipment in there, but that equipment is the source of a lot of the harmonics. So it may well be that you have all of these racks of equipment which are causing high harmonics, which in turn can cause very high levels of neutral current, because if you have multiple harmonics at multiples of 3, they will cause excessive neutral current because all the current flows back in through the neutral. So you can often have 3 times as much current in the neutral as you do on each of the phases. So that would 3 times phase current in the neutral. And if that happens, that can cause the neutral to overheat, and it can cause damage, and in worst cases, it can fail. So again, more tolerances of harmonics. Here we have an example of the harmonics across a whole long period of time, presented as a set of green bars. These are all green bars on here, but we have a limit line. So with the limit line, it tells us that we're in good shape in this case. So the harmonics are not too high. We do have one harmonic there, which is kind of creeping up towards the limit, which is the ninth harmonic. But overall, we're in reasonable shape. It's not causing too much of a problem, and won't really be an issue for us. But what the limit line is doing is that each of the levels for all the harmonics is different. So, for example, the third harmonic level and the fifth harmonic level have a similar magnitude, so that they will be within the region of like 3% each. But as you go up through the harmonics, the levels become much lower as to it being acceptable. So it may well be that a 25th harmonic is only 1%. But this graph correlates all that in one picture. You don't have to worry too much about exactly what the level is for the harmonic itself, because the limit level effectively moves with each of the bar graphs to simplify the analysis. So finally, just looking at some reporting. So once you have your pictures and you have the information that you're really hoping to share, then you can start to build a report. In this case, we have a way of reporting where we capture all the bookmarks and we put them into this kind of view. And then once we've been through the data and done the analysis, we walk through it and then create a report like this, where we just drag over into the right-hand side there, which items we need, and we can build a report which can be 1 or 2 pages, or if you have somebody who needs to know everything, it can be many pages. Depends who your audience is. Always choose, what's going to be meaningful for the audience that you're going to share the report with. And here's a quick kind of rundown on what a good report layout should look like. So things like where and when the study was performed, information about what you were doing. So, the purpose of the study and the details and any findings of the study, have all that information in there. So put that up front so that the person you're sharing it with doesn't have to read through everything necessarily. Make sure you include details of the circuit that you were connected to when you made the study. Also, if possible, take pictures. They're always really helpful. They're helpful for a number of reasons. One is they're helpful to get people into the idea of what this study looked like and where you were doing it. But also, when you come back to it later, you'll remember that more easily when you have the pictures. And if you do a repeated study, you'll be able to really copy exactly what you did the previous time. You should also make details and instrumentation that you use for the study to make sure that you're using the same kind of measuring instrument and that it's going to provide you with similar results. Also, I would say this every time, is make sure that you choose the right time to make measurements over. We have some products which can measure values every quarter of a second, and we get customers who come to us and they say, we've ended up with gigabytes of data because we measured for a quarter of a second for 2 weeks, and they end up with a huge amount of data and it becomes difficult to handle. They don't necessarily need quarter-second data for that length of time. If you're doing a short study, a quarter-second is great. But if you're doing a long study, you should always be thinking in 10-minute periods, because that's kind of what the power quality standards around the world suggest, is 10 minutes. Nothing's really happening that much in a period less than that. There may be dips which are captured in a different way. It's not that you're going to miss those because you measure without any gaps, but having power data and that kind of information, 10 minutes is just fine. You should also add any summary data where it's available. So if you have power quality summaries and so on, you should include those, because they can really kind of make the report a lot quicker and simpler. And you should always put important highlights from the study where you have the ability to compare one thing with another, make those comparisons, include those. And then additional backup data is required. So if you have some other information about what went on at a particular time you're doing the report, then add that. And most importantly, using the same process every time will mean that you'll get into a set of good practices and that you'll make reports every time that look the same, so that people get used to reading them. Also, it's a good discipline for yourself to make sure that you create consistent reports. So just a quick word on exporting data. So this is a way of sharing data with people who aren't using the software that you're using. And often that can be a problem, because sometimes you may have a software package that you've paid for one license and you can't share, but most of the packages have the ability to export the data. And the reason for exporting is that there's lots of other software packages out in the world where that can be used for modeling and planning. So, you know, that data can be used for things like power factor correction calculations, network planning, system modeling, mitigation calculations. So if you have power quality problems with harmonics, when you need a harmonic filter, the person who's going to help you with designing the right harmonic filter needs the data that you've captured. It can also be used for safety planning, so you can make sure that if you're worried about PPE and making the right calculations for NFPA, then this is helpful data and can be exported to other packages, which will allow those calculations to be made more easily. So just to quickly summarize, you know, what I would say is document as much as possible before the survey. Define what the purpose of the survey is. You know, investigate where you're going to be connecting up. Make sure that that place is the right place for you to be working. Make sure you have the right PPE. Also, check to see whether the people that you're sharing this information with are going to need it in another format. You know, just do the pre-work is really important. Then define what measurements you're going to need and make sure that your instrument can do that. First of all, you know, we have customers who come to us after the event and they say, oh, we really wanted this thing. And we said, well, the instrument doesn't do that thing. You know, they wanted some other special measurement. You know, check on that before you go there, because you can end up being very disappointed after a week or two. Make sure you capture the details of the instrument, which I already mentioned. And then when you're ready to start the survey, make sure you've connected up the right way. That is the single most irritating thing for customers. They do a survey for 2 weeks and then they come back and they say, this is really weird that we had negative power on one of the phases, and they just made a silly mistake where they put the current sensor in the wrong way around. Making sure that you've got that right in the first place can save an awful lot of time and heartache. If possible, it's always good if you can just make a check on your log data before you leave it for a long time. If you can do that, that's really helpful. What's even more helpful is downloading the data as often as possible so that you can get some early results, and also to make sure that things are looking okay. Sometimes you can pull your logger out early because you've got enough information. So that if you can get to the logger and you can see the results early, that can be helpful. And then once you've finished, get your data out of the instrument, create a backup. That is, you know, one thing I'd always recommend is make sure that you have a place where you store all your results before you do anything with them. And then the first thing to do is walk through the information with using the software and think about the story you're going to be tell. And then once you've done that, you'll be ready to really dig into making a good report. And then start to create views of the data that tell the story, and either bookmark those pictures or capture screenshots, and creating as many views as makes sense as you go along. And by creating those standard reports and doing the same thing every time, you'll create some consistency in your work and make as many comparative views as useful. And the tables, as I mentioned, can summarize a lot of data all in one place. Making comparisons is always important, and also looking for the exceptions is important, and then building that into the story. And then finally, the most important thing, create an action plan based on your findings. This could be extra measures to save energy, it could be for installation of power mitigation equipment, or it may well just be, right, okay, the study looks okay, we'll plan to come and do this thing again in 3 months, 6 months, or a year, depends what your real need is. So having that final action plan, you know, it's great doing all the right measurements, but at the end, make sure you've done something sensible and actionable about it. Okay. So that's the story.
Thank you, Frank.
Okay.
So now we're going to get into the question and answer portion of the webinar.
Okay.
And you that are not interested in sitting through the questions, my contact information is on this last slide. And you will also receive a follow-up with a link to the recorded webinar. If you have any questions, or if you didn't have time to submit a question and you want to submit something afterwards, feel free to send it through to me, and I'll work with Frank to get your questions answered. Okay, so the first question, I'm not sure I fully understand it, but hopefully you do, Frank. How do you share the data for other opportunities, and in what areas do you see the opportunity by sharing information? Does that make sense to you?
Could you just repeat that, please?
Yeah, I'm going to do it word for word. How do you share the data for other opportunities, and in what areas do you see opportunity by sharing information?
I see. Okay. So if the places where I see data sharing going on is if you're involved with other bodies like consultants and so on, or if you're involved with a client who maybe has asked you to do a study. So really you have to share the data with them so that they effectively see the value of what you're doing for them. And if you're working with consultants, it may well be that they're using a package like ETAP, which is a modeling package, which is a very high level package, which will allow those consulting engineers to kind of take a look at a facility and kind of simulate exactly what's going on in the facility, and then they can add planning value to that. So they will be able to tell you what you should be doing next. The places I've seen that being used are in large facilities. One that comes to mind was a casino, was a huge casino, where they were always moving things inside the casino, different kinds of machines and different kinds of equipment, and they were really concerned what effect that was having, because they didn't want moving those loads around to cause problems. So their opportunity there was they made the measurements, they shared with the consulting engineers, and then they could advise them as to what was the best route to go next. So that's kind of where the opportunity was really making sure that they were doing the right things with the right equipment and they weren't going to create problems further down the line.
Okay. Next question. What causes harmonic distortions?
Okay, so the primary cause of harmonic distortion is electronic loads. Now, there's many types of electronic loads. They can be as simple as a switch mode power supply load, but they can also be things like variable frequency drives. There could be UPS systems. It's any electronic load. They will always cause some amount of distortion. Now, the level of distortion that they create will be dependent upon the quality of the equipment and how well the manufacturer of the equipment has designed their equipment. So often manufacturers will put lots of filtering on the front end of their equipment to make sure that they aren't going to cause distortion, or to make sure it's within an allowable level. And there are standards which dictate what is allowable, but sometimes you may get a fault in a piece of equipment, maybe a filtering capacitor fails on the equipment, so that can cause extra distortion. Or it may well be that the manufacturer is not that a reliable manufacturer and they haven't really taken measures to ensure that the device is filtered properly. So that often depends upon kind of the cost point of the price of the equipment, to be honest. You see kind of cheap imports where they haven't really taken the time to spend money on the filtering on the input, and they become very noisy loads. But the electronic loads are so kind of universal now. Everything inside a plant has some kind of electronics. If it's automation equipment you've got, you'll have switch mode power supplies on PLCs. You'll be driving you'll have drives which are operating with things like gate operated thyristors or electronic loads, and they all take out those gulps of current out of the system, and they cause current distortion, which in turn can cause voltage distortion.
Okay. Next question's a little long. I work with generator paralleling systems, and I have a customer that during the time that we have generators paralleled with the utility and ramping load from and or to the utility, we trip a bus tiebreaker on a ground fault. This problem only exists while the utility and generator sources are connected together. It is believed that we have a positive sequence voltage imbalance, but still need to prove this assumption. We are using a Fluke 435-2. What would be the best method for which to measure this possibility?
Wow, I'd have to take that question offline, I'm afraid, because that needs some real thinking about.
Right.
So what I advise you is that if you email Nicole with your details, I'll make sure that somebody comes back to you.
Okay. All right. That one's
I hope
for
that's
Chris.
okay. Yeah. Okay.
Okay. The next question. Someone's asking about a graph. So they followed up with two questions. So where was the last graph screenshot taken from in the reporting software, specifically voltage harmonic graph versus current as a sine wave screenshot through a single or very few cycles?
That was taken off one of our standard products, which is a 1736 or 1738. But I just captured that. We have a thing called a power quality simulator, which I can simulate third harmonic. That was from 1736 and 1738 products.
Okay.
And it's a simulated picture. I would just mention that.
It's a simulated picture.
Well, it's not a simulated picture. It's a piece of equipment that we get to simulate power quality problems. So it has a set of loads, and I can put third harmonic on there, and that's what we could see on the screen was third harmonic, what that does to the waveform.
Okay. And he just followed up and said, yes, he is using the 1738, same gentleman.
Okay.
Okay. How do dips affect electronic circuits?
Okay. So if you imagine when you have a voltage dip, you're taking energy out of the system. And electronic equipment, as I've previously mentioned, it's taking the power in as a sine wave or on the voltage side or as a gulp of current. If you have a voltage dip and the voltage dip happens to coincide with when you're taking the current in, then the energy won't be there to provide that current. And if the dip occurs for too long a time, then the amount of time depends on the kind of quality of the equipment, but you will start to take energy out because there's no voltage there. There's no way to charge up the capacitance that's inside the equipment, which does the conversion. So that's how voltage dips work. There are ways of classifying the voltage dips. There is a thing called the Sabima curve that classifies the way dips occur in terms of magnitude and duration, and it plots them on a graph. So Sabima is a business organization. So they supply computers, business equipment, and so on. And they came up on this idea many years ago now as a way of classifying whether their equipment should operate correctly. And if you're outside of the envelope or the limits, then they will say, well, we can't provide reliable operation. If you're inside, you should be okay. There's also different variations, an ANSI standard, which works in the same kind of way.
Okay.
So it's all about the duration of the dip that matters and how much energy is not available.
Okay, that's all we have for questions today. So as a reminder, if you have further questions or you'd like to find out more about Transcat's product and service offerings, you can contact us at our 800 number, which is 800-800-5001. You can go to our website at transcat.com, or you can email me directly at nicole.vanwert@transcat.com. My information's on that final slide, and you'll also receive the slides in a few days from us. And thanks everyone for joining us today. Thank you, Frank, for the presentation. We hope everyone got something out of the presentation today and that you continue to join us for Transcat e-learning webinars. Thanks, everyone.
Thank you.